Today I plan to solve one of the challenges I left you last week. Let's have a look. I'm going to ask you to look at Atenea. If you look at Atenea, okay, you can go to the chapter on Lie groups. Okay, what I'm going to correct now is just to address the challenge I left. Remember that I had here the video recording explanations on Lie groups and Lie algebra summary slides. And besides this video, which is not in YouTube, there is these slides here. Well, I have the slides open here. Okay. And at the very end of the slides, in the very last slide, we had this final challenge. And the final challenge was classify all two-dimensional Lie algebras and find Lie groups integrating them. And we have a hint, which is first solve exercise on slide 10. So with this video, I also plan to address one of the questions I got by email of one of you guys who asked me to indeed solve this problem, to solve exercise on slide 10. Then I go to slide 10. Go here, slide 10. And here you have slide 10. Where you can say that the question is to compute the Lie algebra of this group here. The group of matrices with this, you have two parameters, A is positive, B is positive, B is any one, and we want to compute this Lie algebra. This is a two-dimensional Lie algebra, Lie group, okay, because it depends on two parameters. And now I want to indeed to address the problem of integrating the Lie algebra. And in the way, I'm going to classify all two-dimensional Lie algebras. Okay, so in order to do this, first thing I'm gonna do is to stop sharing this presentation here. And now I'm going to write in my tablet. Therefore, I'm going to say you goodbye here. I'm going to freeze my image. I'm going to go to the picture. Okay. Now I go and I'm going to solve this problem on slides. So I open notes. Well, first things first, I should share with you guys again, but I'm going to open notes and I'm going to share with you what I want to share, which is just Lie groups and Lie algebras. Okay. Well, that's yesterday notes. Let me open a new section, and well, the title of the section is classification of two-dimensional Lie algebras. Okay. Okay, all right. So, well, before this, now I got used and addicted to this yesterday. I'm going to write in red with this. Okay, so first, I want to compute the Lie algebra of the group on slide 10. This is the hint indeed. And here A is a positive and B is any real number. Well, first thing first, what is the Lie algebra? The Lie algebra is just a tangent space at the identity of the group. And the identity is just the identity matrix. Okay, because observe that this group, particular group, lies inside the linear group over the reals. Okay, and that's the end. So the thing I need to do is I need to integrate. Okay, so in order to find, I need to find generators of this Lie algebra, expectations is to have to get two generators of the algebra, and then what is the Lie structure or the bracket? As I told you 2 videos ago, the bracket is just given by the commutator of matrices. So once I have the generators, I can compute the constants, the structures of constants of the Lie algebra just using the commutator. So the bracket, when I just take a group which is inside the linear group, the bracket is just the commutator of matrices. Okay, so that's what I need to do. Okay, so observe, what I need to do is to take vectors which are going to be, so curves inside G, which, okay, I need to take curves through I need to take, consider gamma alpha of t. I'm going to take a curve in G such that alpha 0 is the identity, so it's just 1, 0, 0, or 1. That's what I need. And then I'm going to look at alpha prime of 0, and this is going to give me a generator of the Lie algebra. As simple as that. And I can look at this in general, or I can just change the generator. In general, alpha of t is going to be of the following type. It's going to be alpha 1 of t, alpha 2 of t, 0, 1, where alpha 1 of t is always positive and alpha 2 of t is any. That's what I need to think of. Then when I look at the derivative, then what I also need to impose that alpha of 0 is the identity. Of course, this is going to impose that alpha 1 of 0 is 1 and alpha 2 of 0 is 0 in particular. And I need to compute that alpha prime of t, which is going to be alpha 1 prime of t, alpha 2 prime of t. This is going to be the vectors, the tangent vector, okay? 0, 0, and then when I evaluate at 0, I get alpha 1 prime of 0, alpha 2 prime of 0, 0, 0. All right? Now, if I think of generators, I may want to detach alpha 1 from alpha 2. It's convenient. And I can get a generator from alpha 1 and another generator from alpha 2. So now I'm going to consider two different generators. let's think. I may consider the first one. For the first one, I can consider alpha 1 of t equal 1 something, which evaluated at 0 gives me 1. So I may consider something like this, the exponential. What about that? When this is a solid solution and alpha 2 of t equals 0. This gives me one generator where the curve I'm considering, so this is alpha. Let me say that, okay, this gives me one generator. Let me call it alpha. That's okay. And okay, yeah, for this choice of alpha 1 and alpha 2, alpha of t, it's going to be et 0, 0, 1, which is entirely contained in the group. Do you agree with me? And alpha prime of t, it's going to be the exponential 0, 0, 1. And alpha prime 0 is going to be just the identity matrix. Okay. Well, sorry, not the identity matrix. I made an error. Let me erase. Here, when I do the derivative, when I do the derivative of this guy, there was an error here. I get a 0. All right. So let me go back here. I was writing in this one. So here I should write a 0, and here I should write a 0, because I'm just taking the derivative. You agree? So that's one of the generators. A different solution, so this is generator 1. And I may call this guy x. Why not? And let me complete the generator 2. Well, I may consider alpha 1 of t. Well, this guy here has always to be, like, I may consider an element of the group of the type 1, because this has to be positive. I cannot consider 0. I may consider alpha 2 of t equal to t, and then the alpha I'm considering, which I'm going to call alpha tilde of t, it's going to be 1 t 0. You may ask yourself, why don't you put a 0 here in alpha 1? Yeah, because this is not a solution. I need an alpha 1 which is strictly positive. So I take this 1. Okay? Never mind, because when any positive number could make, because when I'm going to do the derivative, this is going to be 0. But what is important to notice is that this guy is inside alpha, lies in the group. The same as this alpha t, lies in the group. That's what I'm aiming at when I do this guy here. Now I take alpha prime and I get 0, 1, 0, 0, 0. Do you agree with me? Okay, and in particular, when I evaluate at 0, I get 0, 1, 0, 0. I may call this guy y. So this Lie algebra I may consider matrices of this sort. Okay, and this Lie algebra is generated by x and y above. So let's compute the bracket. Why do I want to compute the bracket? Because so far what I have so far is the vector space structure, and I need to put Lie algebra structure, so I need to compute the bracket. I said I'm going to compute the bracket, so I have x is this vector, is this matrix, and y is this matrix. And the only thing I need to do is to compute, in order to compute the bracket, is to compute the commutator. All right. So I compute the commutator. So here I need to make the product of these matrices. All right. And the commutator gives me tachan 0, 1, 0, 0, and this goes to 0. So the commutator gives me y. So I have a Lie algebra, two-dimensional, such that xy equals y. So that's the edges I solve. So what are the Lie algebra structural constants? Remember that these constants, if I have a basis of the Lie algebra of type xy, the notation is the following. If I take two elements, then I denote the sum of this. I put a subindex Gij and superindex xk, and I denote this from k1 to n. And these guys here are called the structure constant. Okay, so here I just get in our case, okay, then I have that x is x1 and y above is x2. Therefore, there is only one of them. So I have C1, 2, super 2 is equal to 1, and the rest are 0. Observe, remark that I'm going to do. This Lie algebra is non-abelian. How do I know it? Because if it was abelian, then all the brackets are always 0 for any couple of elements. So this is a non-abelian Lie algebra. Okay, so that's the exercise. That's how I compute the Lie algebra. Okay, just by taking a path of elements in the group and doing the derivative, just by taking the definition of Lie algebra. Is that clear? Okay, now next step, I use this example as motivation for classification of Lie algebra. So now it comes the guys with the big guns. Okay, so now we go and choose a very nice color for this, a pinky color, and I'm going to put it bigger. So now here we go, classification of two-dimensional Lie algebras. That's what we're going to do here. Okay, so what we are going to do a little bit is just to play the same game as we were playing above, knowing that we're going to have, so the starting point just trying to play similar game. We have two set generators. Okay, so I'm going to call them x1 and x2. Okay, and now I use, well, what is clear is that if I have an element with itself, this is going to be 0, and this is going to be 0. Therefore, from this, you can read a bunch of, you know that Zii super k is always 0. That's what I'm saying. This is nothing new. Now I want to look at this equation. It's essentially, if we're in dimension 2, what I'm saying is that that's the only equation we need to look at. Okay, indeed, that's the only equation. That's the only equation governing this classification of Lie algebras. And that's what we need to understand. And these two elements here, I'm going to choose the notation, the standard notation, okay, from Lie algebras, which is that this is going to be C1, 1, 1, 2, sorry. This is C12 super 1 x1 plus C12 super 2 x2. That's what we have. All right. So, stupid remark, or well, not stupid, but let's say first remark. The case in which both of them are 0, then the Lie algebra is abelian. Okay, and then there's nothing to look for. We already have that the Lie algebra is abelian, and that's all we have. So we may assume that one of them is no 0. So assume one of them is non-zero. Okay, so let's assume, for instance, that the first one is non-zero. Okay, we may assume this. If it's the other one, then we change the order. Okay, now consider a new basis. Okay, which is given by y1 equal C consider this change of coordinates. Okay, so this y1 is an element of the Lie algebra, and y2, as we are assuming that the first element is different from 0, do this change of coordinates, and after doing this change of coordinates, I'm going to leave you like as a simple computation. That I want to leave as exercise. Okay, tells me that the bracket of y1 and y2, like we can do this bracket as exercise, equals y1. Okay, and that's the second big case that we have. If we compare to the choice we took here, we have here that x1 and x2, x and y give me y, but you may change the order of x and y, okay, and you get exactly that this is like the Lie algebra, okay, you get exactly that this is the same case by changing coordinates. That's the same algebra. That's the Lie algebra of G. And that's non-abelian, that's non-commutative, and that's the only non-commutative, because if you have another non-commutative Lie algebra, one thing you can do is to do this change of coordinates. Okay, so summing up, we have proved the following theorem. Classification of two-dimensional Lie algebras. There are two-dimensional Lie algebras. The first one, which is G with a bracket equal to 0, this is the abelian. And the second one that you can present as the Lie algebra of the element of the previous example of G, or you can present as an algebra of two generators, x1 and x2, or y1 and y2 if you want. Okay, with bracket y1 and y2 equal to y1. That's the theorem that we have just proved in the session of today. Then a natural question is, what are the Lie groups? I mean, do we have more than one Lie group integrating these Lie algebras? Well, remark that in the case of the abelian Lie algebra, we have different. We have R2, okay, we have S1 times R, okay, and we also have the S1 times S1, okay. This would be three Lie groups integrating three Lie groups. Integrating the abelian Lie algebra. And well, we have the other group as an example of Lie group integrating the non-abelian. We have the example with it. And we can prove that this is the only connected non-abelian Lie group in dimension 2. Okay, the non-abelian case. We have the Lie algebra of G, where G is the set of matrices. Okay, and the remark is that we can prove that this is the only This is the only connected, not abelian Lie group of dimension 2. Well, that's all I wanted to say. Thank you very much for your attention. And I'm going to stop the presentation. Okay, I'm going to recover. I'm back here. Okay, what I wanted to say is that's all I want to say for today. So we managed to classify all the algebras which are two-dimensional. Thanks a lot for your attention. Our next piece of Lie groups and Lie algebras will come soon.